Today I'm talking about algorithms for redistricting. Redistricting involves dividing a geographic region into districts, each of which elects a representative. Now, in the US, the Constitution assigns this job to the state legislature, which creates some problems because the state legislature can choose to use this power to gerrymander, to achieve some unsavory goal through engineering those districts. Fortunately, in the US, voters have shown their opposition to gerrymandering, and in many states, redistricting is in the hands of independent, nonpartisan or bipartisan commissions. The primary goal of our research is to put sophisticated computational tools in the hands of those who seek to redistrict without gerrymandering. A secondary goal is to provide provably correct algorithms for uniform random sampling of district plans. This has been used in court challenges to gerrymanders. The immediate motivation for our research came from France, where there's a plan to change the state legislature. That's going to require redistricting. Another research team, including one of my co-authors, sought to enumerate all the legal plans, and they succeeded for many of the departments in France, but not all of them. And that prompted this research project. We wanted to see if we could use algorithms to find optimal plans for all the departments in France. Now, a redistricting should satisfy the following criteria. The population should be balanced, each district should be contiguous, and the districts should be compact regions. There are multiple definitions of compactness. Today, we're going to focus on a particular kind of problem. I call it discrete coarse redistricting problem. The state or department to be redistricted is made up of atomic regions, and a district plan must be a partition of these regions. So the goal is to find a partition into k parts that balances population to within a given tolerance. That defines the population balance. We want each part to be connected, and that'll satisfy contiguity. And finally, we want to minimize the cost of the cut edges. And this is our version of compactness. So what's a cut edge? Let's say you have a district as shown here. Then the cut edges corresponding to that district represent pairs of atoms that are adjacent in the map, but are in two different districts. So here are some cut edges. And this has been proposed as a measure of compactness. Now, a related goal is to uniformly sample from feasible partitions. Okay, these are NP-hard problems. So what can we do? Can we restrict the input to make the problem easier? We're going to look at branch width, which is a way of cutting up the graph. So because these graphs have, the graph of atoms has small diameter, it follows that these graphs have moderately small branch width or tree width. Previous authors, motivated by redistricting, looked at uniform random sampling of k-way connected partitions and gave a theoretical algorithm that ran in n log n time. Now, this ignores population balance. By the way, the big O constant depends on k, the number of districts, and w, the branch width. And such an algorithm is said to be fixed parameter tractable because it's bounded by a polynomial whose degree does not depend on these parameters. And they ask whether this can be extended to require population balance, and the answer is no. So on the one hand, there are these n log n algorithms if you don't care about population balance, and these are fixed parameter tractable. But we can show under a standard complexity theory assumption that the corresponding problems in which population balance is required are not fixed parameter tractable with respect to the two parameters w and k. On the other hand, these problems are fixed parameter tractable separately with respect to w and with respect to k. And we did an implementation and found that the algorithm is usable, and we used it, in fact, to find solutions for all the French departments.